Okay. Miss Darren. Done?
Yeah.
Okay, so we have done velocity analysis by velocity polygon method and also by instantaneous surface method. I understand some of you have difficulty in identifying the instantaneous centers. Can you see the figure here? So here this, see it's a 4-bar linkage mechanism, right? So you can see instantaneous center 1, 2 here, 2, 3 here. So this is link 2. Okay, this is link 3. So 3, 4 is here. So 3, 4 is the connecting rod with the piston, which is link 4, the slider. Okay, so now 1, 4 will be perpendicular to the horizontal here. Okay, 1, 4 will be at infinity because 1 and 4 you are referring to 2 parallel lines. So 2 parallel lines will never meet. Okay, 1 is the ground link and link 4 is also having the movement along the same ground link. So therefore, the instantaneous center for 1 and 4 is shown as infinity and it is perpendicular to the incline. So the horizontal movement, because the piston can only go horizontal. So the instantaneous center for link 1 and 4 will be at infinity. So we have discussed this in the earlier section. So now if you see here, the slider is at an incline. Okay, link 2, link 3, link 4 is the slider. Now the instantaneous center for 3, 4 is shown here. Now the 1, 4 will be at infinity, okay, perpendicular to the incline here. Okay, so now 1, 4 at infinity, 3, 4, so 1, 3 will be on this line. So 1, 2 is here, 2, 3 here, so 1, 3 will be on the line. So the intersection point will be on the line. So whenever we have the same point, okay, 2 points which can, okay, move horizontally or then the instantaneous center will be at infinity. And many times when a slider is moving along the ground, okay, the instantaneous center is perpendicular. So in the same way in the previous example which we have done the 4-bar linkage system, so the instantaneous center there, the link 4 is moving vertically up and down. So the instantaneous center will be at infinity, perpendicular to the movement of the link. Alright, so this is, you have to recall this. Okay, so next we move on to the acceleration analysis. So the acceleration analysis is similar to the velocity, relative velocity analysis. So we write acceleration of V is acceleration of A plus B to A. So I'll just write before. So for 2 points, so we can write the acceleration of V is acceleration of A plus acceleration of B to A, right? So when we talk about acceleration, then there will be 2 components for acceleration because we are dealing with links which are moving in circular motion. Okay, So the links which are moving in circular motion. So when you consider a 4-bar linkage system, okay, I just draw a 4-bar linkage A. So let us say B. Let us say C. Okay, so we are trying to link the 2 points A and B. Okay, now for acceleration of A, will have, because this point can move in a circular motion like this. Okay, so at this point, at this position, so the acceleration will be depending on the angular acceleration of the link. Okay, depending on the angular acceleration of the link. So there will be 2 components. One is the tangential component and the other one is the normal component. Let us consider the angular acceleration alpha 2 is clockwise. Okay, and the tangential component will be perpendicular to the link like this. So we can write now acceleration of A. This is the tangential component. Okay, and the acceleration of A normal component will be in this direction. So this will be acceleration of A normal. So normal and tangential component will be perpendicular to each other. Okay, so normal component will be in this direction and tangential component will be perpendicular to the link. And again, this one is downwards like this or upwards like this, depends on the direction of the angular acceleration of link 2. Okay, so now consider point B. Okay, now acceleration of BA normal will be like this. So this is acceleration of BA normal. Okay, acceleration of BA tangent will be perpendicular to the link. So link AB. So this is BA tangent. So BA normal and BA tangent will be perpendicular. So now acceleration of B normal. So acceleration of B normal will be in this direction, the direction of link 4, acceleration of B normal. Then acceleration of B tangent will be perpendicular to the link 4. Okay, so now we can write the relative acceleration equation. Acceleration of B tangent plus acceleration of B normal is equal to acceleration of A tangent plus acceleration of A normal plus BA tangent plus BA normal. So this is the equation, relative acceleration equation. Now out of this equation, we know completely the information related to acceleration of A tangent and normal. Okay, so you know the direction and you know the magnitude. Similarly, normal, you know the direction, you know the magnitude. So direction is known, magnitude is known. So that means for point A, we know the complete information. Now when you come to B normal, so B normal, we know the direction and magnitude, because normal is r into omega square. Okay? So when you start acceleration analysis, you know the angular velocity of all the links. So therefore, you know the direction and magnitude of B normal. So B tangent, we know only direction. So BA normal, we know both direction and magnitude. and BA tangent we only know the direction. So that leaves we need to know now two things, which are the magnitude of AB tangent. So we should know the magnitude of AB tangent. So we need to find out this. So similarly, BA tangent magnitude. So we need to draw now the acceleration polygons for all the known things and complete the polygon and measure acceleration of B tangent and acceleration of BA tangent. So because you know the magnitudes and the directions of all other things, right? So therefore you should be able to plot to complete the polygon. Just like the velocity polygon, now you have additional components, tangential component and normal component. The good thing is these two components will be perpendicular to each other. Okay? Because you already know the directions of all the links. So the normal accelerations will be always in the direction of the link. So the directions of normal components. Magnitudes also you know because you know angular velocities. Okay? So for example, what is the acceleration of A normal component? So you can say OPA into omega 2 square. So similarly, normal acceleration is simply A normal is R omega square. So since we know angular velocity, so the normal components, then the tangential components, the acceleration is perpendicular to the norm. So that means perpendicular to the link. Whether it is upwards or downwards, we need to decide. Now, for example, BA tangent. Now, if you look here, BA. So BA tangent will be perpendicular to AB link. Okay. Whether it is upwards or downwards, we need to decide. But once we complete the polygon, we can understand it. So for the given orientation, the point BA, the tangential acceleration is upwards or downwards. Once you complete the acceleration polygon. Okay, so this is basically the theory part is only the same. Okay, this equation. Unlike velocities, here you have normal and tangential. So you are again plotting the acceleration polygons. All right. So now, for example, now we'll try to understand. So this is the data given to you. Omega 2 is given to you, angular velocity, and alpha 2, angular acceleration is given to you. So the orientations of both are given. Okay, so consider that all the information is given. Omega 3 is given. It is not given, but once you do your velocity analysis, so you know angular velocity of link 3 and also angular velocity of link 4. Okay, so by doing velocity analysis, you know these two values. Okay, now the question is now find the acceleration of point B. Then acceleration of point C, which is on link 3, then angular accelerations of link 3 and link 4. Okay, so these are the unknowns we need to calculate by drawing the acceleration polygon method or the relative acceleration method. Is the question clear? Okay, so because the angular velocities are all given, so we can do first the calculations of all normal components. So for A, we can easily calculate the tangential component and normal component. So we write the equation here. Acceleration of B is acceleration of A plus acceleration B to A. So now we include the normal and tangential components. So for B, both normal and tangential. A also normal and tangential. BA also normal and tangential. Okay, so normal acceleration you can calculate VA square over O2A. So you can use either of the formula. You can use R into omega 2 square, or you can also use VA square by O2A. So VA we know, so O2A we know. So now the normal component of acceleration we know. Then the tangential component, so is simply O2A into alpha 2. Alpha 2 is given to us, so we know the tangential component. Okay, so now when you want to plot, so the normal acceleration is plotted as 3000 mm per second square. The orientation of this is in the direction of the link. Okay, now you know the direction of the link already. Okay, so point A will have a normal acceleration towards O2. Okay, and tangential acceleration is perpendicular to this link. You know the magnitude. So that is what is plotted here. So from the origin, so acceleration of A normal is plotted. Okay, then perpendicular to this is acceleration of A tangent. We know the magnitudes of both. Okay, so you plotted this vector, acceleration of A normal, from the tip, you draw acceleration of A tangent. Now when you join these two, you get acceleration of A. Okay, so this is the acceleration of A vector. Alright, so now we calculate BA normal. So BA normal is velocity BA over BA square over AB. So BA square also we know from velocity analysis. Okay, AB is given, so you know acceleration of BA normal. So acceleration of BA normal will be in the direction of the link BA. So if you see, this is the direction of link BA, right? So BA normal will be in this direction. Okay, so that is what is drawn here. Okay, the formula is you are adding acceleration of A plus BA normal and tangent. So you have to add to this point acceleration of A, then BA normal, we know magnitude and direction, then perpendicular this will be tangent, BA tangent. So we'll add BA tangent, we don't know the magnitude, but the direction is just perpendicular to this. So that is what is drawn, BA tangent. Perpendicular to BA normal. Okay, so now we have done this A normal, A tangent, we have done BA normal, BA tangent, we have done. So now we move to the horizon. So we now draw B normal and B tangent. So B normal, we know the magnitude and direction. So for example, B normal, the magnitude is VB square by O4B. Velocity B square we know from velocity analysis. So the magnitude of B normal is 376. So the direction of B normal will be along the link. So from position analysis we know the directions. So we know B normal. So this is B normal is plotted. So the magnitude is 376. So this is B normal. Now B tangent will be perpendicular to B normal. So now you just draw a perpendicular line to this and let these two join. So you can now find the intersection point here. So now the acceleration polygon is complete. Guys, any questions here? I'll pause here for a minute. So these two dotted lines or that construction lines are the directions of BA tangent and B tangent. And we are plotting this acceleration polygon as per the relative acceleration equation. Any questions? serious discussion is going on, Prabhu. There are two involved. Again, you are looking at it. So, what is that? You can share with us. Any question related to this? Are you worried about something happening in the world? Okay, all right. Is that clear? The acceleration polygon. So the concept is always we are linking to points. So make note of that. So A and B, now the polygon is complete. Now you can read the magnitudes from the polygon, from your drawing. Now this analysis you can extend to any number of points. So that means now you know complete information of point B and A. So now you want to find out C. So you can link now the point A and C or point B and C. And again draw another polygon to know the remaining things. Okay, so now we are linking, okay, so acceleration of B you measure, now you are closing this, okay, so you are closing this. So that is measured acceleration of B. Then similarly BA tangent. So you can measure this is BA tangent, only this much. So your acceleration of BA normal, BA tangent. So you join these two things, so that will be your acceleration of B. So the black arrow. Okay. So acceleration of A vector, BA normal, BA tangent is equal to acceleration of B. So BA tangent you can measure the magnitude, so that is about here. Okay. Then you can calculate your angular acceleration of link 3. So link 3 is BA tangent over A. Okay. So from this you can know angular acceleration of link 3. Then you can also calculate link 4 angular acceleration. So you know B tangent over O4B. So that gives you angular acceleration of link 4. Okay, so your complete acceleration polygon now looks like this for point B and A. Okay, so now you are linking point C to point A. So link point C to A, so you can again write C normal plus C tangent is A, acceleration of A plus acceleration of CA. Okay, so you know already acceleration of A, therefore you are plotting acceleration of A. So you know this information, so you are plotting acceleration of A. Then from the tip of this, you need to plot CA normal and CA tangent. So these two will be perpendicular to each other. So CA tangent you can calculate alpha 3 into AC. So AC, the distance, you know, so it is tangent is perpendicular to this. So you can calculate the magnitude of C tangent, and of course you also can know the orientation of that. Okay, so now from the tip of A, acceleration of A, you are plotting acceleration of CA tangent. Okay, then CA normal also you know the magnitude and direction. So it is velocity is CA square over AC, and you know the orientation. So you know the complete information of CA. Okay, so this is acceleration of A, then tangent and normal is drawn CA. So this is acceleration of C. Yeah. So this is how you can do acceleration analysis. Always start from point where we know complete information. So that is always the link to the point on link. Then link that point to B or any point on link. Then apply the relative acceleration equation. Then resolve normal and tangential components. Okay. When you do acceleration analysis, you need to have all the velocity information ready with you, because you're calculating the magnitudes of normal acceleration for B, BA, okay? Then the directions also. So the directions of tangent will be just perpendicular to normal. So you try to draw the perpendicular lines, then intersection points find out, fix, then you'll be able to establish the tangential components of BA and B tangent. Then you can calculate angular accelerations of alpha 3 and alpha 2. Alright, so the acceleration analysis is an extension of your velocity analysis. The T is the same, the relative acceleration analysis. We are drawing the coordinates. And luckily this is the only method, so there is no instantaneous LTS method for acceleration, only for velocities. Again, the more you practice, you can easily do the examples. So there will be one question on acceleration analysis. Alright, acceleration analysis has one more component which we have not discussed. So that component is known as this Coriolis acceleration. So Coriolis acceleration is sometimes, as you can see, this is the third acceleration. So you can see as the slider is moving and also as the link is rotating. Okay, so you can see the orientation of the directions of the slider will be changing. Okay, so this is very similar to the winds blowing from east to west as because of the Earth's rotation. So as if it appears that the winds will just change their direction. Okay, so this is known as the acceleration, Coriolis acceleration. So this happens when sliding contact occurs between two rotating links. So now the link 2 is rotating and also this link 3 is rotating and the slider is also having a movement. So under these conditions we have the third component of acceleration known as Coriolis acceleration. So you can see a bit more on Coriolis acceleration from this figure. So now there are two instances. Okay, there are 4 instances you can see here. In the first case, so we have a ground link 1, link 2 is this rod, okay, then link 3 is the slider. Okay, so here in this case, now the angular velocity is clockwise. Angular velocity is clockwise. So in this case, the Coriolis acceleration is Q2, or the relative acceleration of C3 and C2. So link 3 and link 2. So link 3 is the slider. Okay, and the relative motion of the slider is shown here. Okay, so this is 90 degrees clockwise. Now the same thing, angular velocity of link 2 is clockwise. Okay, but now the slider is in this case the slider is going up. So here the slider is coming down. So in this case the relative acceleration changes the direction, you can see. So this relative acceleration is called as the Coriolis acceleration. Okay, Coriolis acceleration of point C on link 3 and link 2. So it points to perpendicular to the link 2, but it is the other side. Now here the bottom 2 diagram shows omega 2 is counterclockwise. Omega 2 is counterclockwise. And now the slider in this case is going up. Okay, and in this case the Coriolis acceleration is as shown the point C perpendicular to link 2. Okay, so you can call this upwards, but in this case the slider is going down, that means the Coriolis acceleration is perpendicular to the link downwards. So in both cases you can see angular velocity of link 2 is counterclockwise. But here the slider is going up, here the slider is down. So in this case the Coriolis acceleration directions are shown. Okay, so in the top diagrams the angular velocity is clockwise, but the first case slider is going up, and the second case the slider is coming down. So depending on the movement of link 2 and the slider, so the Coriolis acceleration can take perpendicular to the link, of course, okay, but it can be upwards or downwards. It all depends on the direction of link 2 and the movement of the slider. Okay, so this one is pretty standardized. So you have only these 4 variations. Now we need to know how to calculate the magnitude. So the directions we can fix for the Coriolis acceleration. Okay, so the direction now we can, the magnitude is of Coriolis acceleration for 2 points, let us say in this case for point B on link 2 and link 4. Okay, so this is point B which is connected to link 2 and also link 4. So the Coriolis acceleration is 2 times the relative velocity 2v, B2 to B4. This is the relative velocity of link point B on link 2 and link 4 multiplied by angular velocity of link omega 4. Okay, so the Coriolis acceleration calculations will be 2 times the relative velocity into angular velocity omega. So 2v omega. So v is the relative velocity of point between the 2 links. Omega is the angular velocity of the link. Okay, so this is how you can calculate the Coriolis acceleration magnitude. So direction, how we can fix based on, okay, the angular velocity of link 2 and the slider, whether it is moving up or down. Okay, so now let us look at how we can do the Coriolis acceleration. Okay, so now all the data is given for this 4-bar linkage mechanism. So now the point B, okay, the link, the slider 3 is now at this point is on link 2 and also on link 4. So there is a relative velocity of point B on link 2 and link 4. So we know all this data. So from all this data, you need to calculate acceleration of B on link 4, then angular acceleration of link 4, angular acceleration, and acceleration of the point C. So Coriolis acceleration is just a component instead of tangential acceleration which we have done. So instead of tangential acceleration, when we have, okay, a slider is connected to 2 links, okay, then we replace the tangential acceleration with Coriolis acceleration. That's all. So in this case, now we link point B on link 4 with point B on link 2, then the relative acceleration. Okay, so just like the relative accelerations now, because the point B is located on link 2 and link 4. Okay, so we write the relative acceleration equation like this. Now we add the components. So now we add the normal and tangential components for B4, then for B2, okay, for this. Then when you come to the relative accelerations, so we write, so this is the relative acceleration of the slider. So S represents the slider. So C represents the Coriolis acceleration. Okay, then the normal acceleration of B4 to B2 and tangential acceleration, this will be 0. So basically you have the same equation, but the tangential component is replaced with Coriolis acceleration. Okay. So now we have to just, now depending on the links, we need to establish the direction of the Coriolis acceleration. So here the link is, the slider is going down, okay, the angular velocity of is clockwise, okay, this is counterclockwise. So the same thing which I have shown in the previous slide. Okay, this is how we can establish the direction of the Coriolis acceleration. Okay, so then we need to just calculate all those things, then plot the normal component and plot the acceleration polygons as per this equation. Okay, so plot the polygons as per this equation. Okay, so you can go through all these slides. So I already uploaded these things, so you can try to understand this. After this, we move on to the analytical method. So we have done the graphical velocity analysis, graphical acceleration analysis. Okay. So in acceleration analysis, we have Coriolis acceleration component comes in. So that replaces the tangential acceleration when we have a point common to two links. A slider which is connected to two links. Okay. So the next one is analytical solution. So you are assigned that to the first part of the question is the same model. Okay. Now calculate velocities and accelerations using analytical equations. Okay. So how to derive the analytical equations we can simply understand from this example. Okay. So this is a 4-bar linkage mechanism, right? So you can consider this R1. So this is R2, R3, R4. So these are basically the position vectors. Okay. Then theta 2, theta 1, theta 3, theta 4. So the orientations are the position vectors. So that means you know the vector magnitude and you know the orientation. Okay, so then you can write the sum of these vectors. Now, if you see here, R1 plus, okay, this is R1 plus R2 plus R3 should equal to R4. So vector addition should give a 0. Okay, so this is a closed loop. R1 plus R2 plus R3 should equal to R4. Vector addition. So that's what we have written. So now we can represent these position vectors in complex notation. Okay, because we know that theta, the orientation of link 1, link 2, link 3, and link 4. So we can use the complex notation using the Euler's identity. So we can write R1 into exponential power I theta 1. So where I is the imaginary number. So e power I theta means cos theta plus I sin theta. So you know that Euler's identity, right? I will just so you know that the exponential power I theta is, so this is also known as cis theta cos theta plus I sin theta. Okay. So a vector can be represented using this complex notation. So basically you are dividing the vector into its x component and y component. Okay, so we write now the same vector equation by the complex notation. You can write like this. Okay, now you take the derivative of this equation, then e power I theta is I theta into exponential power I theta. So you just take the derivative, you can write like this. Okay, then you can convert this into rectangular form. So take out the real components and imaginary component separately, and omega 2 means theta 2 dot. Okay, the derivative of the angular position of link 2. So theta 2 dot is nothing but omega 2. So similarly, theta 3 dot is omega 3. Okay, theta 4 dot is omega 4. So now you can, from the previous equation, okay, so from this equation you can write cosine terms and sine terms separately. So I told you that the e power I theta can be written as cosine theta plus I sine theta. So that means your cos theta terms are real, sine theta terms are imaginary terms. So separate all the cosine terms and sine terms separately. Okay, so then from the equations you can write omega 3 and omega 4. So in terms of omega 2 we know angular velocity of link 2. So from this expression, so you can calculate omega 3, angular velocity of link 3. And from this expression you can calculate angular velocity of link 4. Now theta 2 is given, theta 3 and theta 4 you can do from your position analysis. Okay, once you plot the mechanism to scale, you know theta 3 and theta 4. Otherwise, you can also use expressions to calculate theta 3 and theta 4. So all the terms are known. So no position analysis required, no velocity analysis is required. You can just use this equation and calculate. But the third thing is that for every type of linkage mechanism, you will end up with different set of equations. Okay, so that means you have to derive these equations first, then do the calculations. So if you want to get rid of the graphical analysis, you can also use analytical solution for a 4-bar mechanism or 5-bar mechanism or 6-bar mechanism. So this is how, in a simple case, so you can derive the omega 3 and omega 4 expressions. Alright, so basically we use the vector addition of all the position vectors to 0 and then use complex notation to derive the required equations for velocities, and later once you know velocities, then you can find out accelerations. Okay, so for all the points on the mechanism, we can apply. Next, we look into your assignment 2. Any problem with your assignment 1? So some of you written, I replied. So your date is fast approaching. So I consider you have no problem. So I gave you all the files, required files online, Canvas. So try to prepare your assignment on similar lines. I can't do. You have to write to Joshua. So because this is done in a, there is a process for that. So that's why I've been telling you from the first week onwards that the best way is to don't work in isolation, work in groups. The best way to do this on time is work in groups, and you can share your information and you can do it faster. Because the methodology is the same. So always 2-3 people can actually, learning is faster. Okay, and normally when you apply for your extension, then you have to submit a user. And they'll also ask for documentation. Okay, so the extension part, don't write to me directly, you can write to the program. Okay, so now the second part of the assignment. So obtain analytical solution for positions, velocities, and accelerations by vector loop equations and complex number notation. and present the results in a tabular form. So compare these results with those obtained using the graphical approach. You should have good correlation. So it doesn't matter whether you have good correlation or not, but normally from my experience I can say that 80% of you can have very good correlation. So in 20% cases there could be some problem because of calculation errors, because you have done some mistakes in graphical methods. But it doesn't matter. Accuracy is not important. What is important is that how you develop your assignment. So whether you develop some good understanding of the assignment or not. Okay. So this is your mechanism, right? So this is the 6-part linkage mechanism. So this is all the information which you know, the length of links, okay, or whatever is defined there. Okay, so now let us look position analyzing the position for joint A. So we just take the link 2. Okay, I will not be explaining all the equations. Only the first part of the equations I can explain. Later you can just use all the same equations. For all of you, the equations will be the same. Okay. So if you want, you can use the same equations, but do the calculations as per your data. Okay. So you can share these equations. You can, instead of typing all the equations, you can follow, or you can share the equations. If somebody has in Word format, you can use these equations. Now just take the length. We know L2, you know theta 2, right? This information is known to you. So this is your ground link. So you are resolving this into x component, which is L2 into cosine theta. Theta is theta 2 here. Okay. So y component is L2 into sin theta. So L2 is known, theta 2 is 60 for all of you, I think. So you calculate what is the y xa, y. Okay. Then take the derivative of this. So x dot a is the derivative of this. So cosine theta derivative becomes minus sin theta. Okay. So the derivative of this is minus L2 theta 2 dot. So theta 2 dot is nothing but omega 2. The derivative of theta 2. So into sin theta. So similarly y. Okay. So theta 2 dot is nothing but angular velocity of link 2. So now from these equations you can write velocity A is the square of the x component and square of the y component under root. Okay, so you can know the direction of this velocity A. Okay, so you can know the direction of velocity A. It is some theta 2 plus 90 degrees. It is perpendicular to link 2, right? So you know the orientation. Okay. Then the second derivative of xa. So that gives you acceleration A component. Here theta 2 dash is nothing but acceleration of link 2. So which is given as 0. Okay. So similarly y double dot A. Okay. Then acceleration A is the square of the x double dot A and y double dot. Okay. So then the angle of this acceleration A, so A is acceleration of A orientation, so you can find from this. So that is for point A. So for point A, using this equation, so you can calculate analytically. Okay, all this information, then you can move on coupler and rocker for points B and C. Okay, so for point B and C, okay, so this is point B and C. So you are linking this point B and C. So we know the Euler's identity, the complex notation e power I theta can be written as cosine theta plus I sin theta. So now you can write RA plus RB, R3. So this is the position vector A plus 3, RE plus R4. So you can refer here what is RA, RB, RC. So this is the free body diagram for position analysis. So the sum of the vectors should be 0. Okay. So that is what is shown here. So rearrange the terms, then you can write the position of AE like this. So you will have the AE real component part and imaginary component part. Then you expand this. Okay. So ultimately you can see this is the expression for theta 4, the orientation of link 4. Okay. So then you can similarly get theta 3 from this expression. Okay. So then continue like this, then you will have the velocity B, this is the expression, then acceleration of B. Okay, you will have a lot of equations, but the main things, so velocity C you can calculate from here. Okay, acceleration of C you can calculate. Okay, then you move on to point D. So point D, theta 5, the calculation is here. Okay. So then you can calculate XD and YD. So velocity of D you can calculate from here. Acceleration of D. Okay, every component the calculations are required. Okay, then you move on to so this is the velocity B. Components for velocity C. So you need to calculate what is XC from this because you know all the data. X dot C you know from this. YC you need to calculate. Y dot C you need to calculate. Then you can calculate these. Alright. So there are a lot of equations you can see. Next, to move on to acceleration. So, omega 5 calculation, alpha 5 calculation. After there are many calculations, you need to finally show this type of table. Okay, so here comparison of results by graphical and analytical methods. So graphical, what is that you got? Okay, analytical, what is your calculation? So analytical means using the equations. Now you can use all these equations. The equations are also available on Canvas. So Canvas, there is a file which is useful for your how to simulate your working model and how to use the analytical equations. So all the equations which I gave are from that file. So the file which is available on Canvas. So you need to prepare a table like this. So you can see here the calculations are very close. Graphical and analytical for angle only. Theta 3, theta 4, theta 5. So similar for velocities. Okay. So you know graphical method and analytical method. So it is 8.29 and analytical also same. So then angular velocities, so then accelerations, then angular accelerations. Okay, so at the end of your assignment, first part, we need to see the table like this. Yeah, but the good thing is just the calculations. And I said if we can sit together and do share your notes. No, whatever the equation, the calculation part is time consuming. Okay, and because you need to show if you want to avoid typing, okay, you can also write your equations neatly. But if you want to share the same equations, cut and paste also can be. But the calculations, the numerical values you must show along with your equations. It's routine, but not difficult. It's quite routine, consumes a lot of time. Let me tell you, nearly 60 to 70% of the students will score full marks for the assignment. So, first part, I think all of you should score full marks. Second part is I know this is the most challenging assignment in the entire course. Basic will be in terms of, if you're getting 10 marks, I can give you 12 marks, 13 marks. That will be there. But if there is nothing, I cannot do anything. This happens in all cases. Particularly for the exam.
Exam calculation. What?
Exam, there are a number of students who scores 50, 45 to 50. But there is a possibility some students
For exam.
10%. Okay, the assignment A1 20%, A2 20%, class test 10%, online class test. So 50%, end of term 50%.
Online class is tricky.
Okay, so end of term exam you will have only 4 questions, 3 hours plus 15 minutes. 15 minutes of course is the reading time. So 3 hours, and that should be more than sufficient. And 2 questions will be calculations or simple. But the first 2 questions, graphical velocity and acceleration analysis. So that will have 60% variation. And there will be 1 question on balancing, which one everybody can do it easily. And 1 question on force analysis is also fine. Alright, so I'll see you. One more thing. If you have any problem